Okay, the recording is on. It's 7:59, which means that I'm going to start pretty much right away.
Hi. Are you available after this class?
I am.
Okay.
Yeah, I am available. I'm not going to go anywhere for a bit. One, I have to have a patch put on my computer, so I got to be here. There is apparently some Wi-Fi as of this morning, but it's in the cafeteria, library, and main office, so it wouldn't be able to reach here anyways. Like out here, or even downstairs, I found that, like in the room that we were supposed to be in, right? I said I'm going to start right away. Maybe I should wait 1 minute for those that went downstairs and then saw the message, right? But I'm going to put this up just to kind of remind you about a couple of things. I'm going to be talking in an unusual voice because I want to make sure that the microphone picks up my voice. And I'm competing with this pipe noise. Yeah, all good. Okay. Thanks for finding our new classroom. The issue is that I can't get the projector to work downstairs, and so this is my short-term solution. No time to find another room. Turn that phone off, please.
It's so stressful to wake up to.
Yeah, okay.
No. This is the hard one. You do tutorial class?
Yeah, I went through it.
Yeah.
Did it get in my head?
Yeah. Okay, so folks, I think I will start. I welcome you under these unusual situations. As far as I know, going forward, we will be meeting live. Hopefully, by Wednesday morning, I'll have the classroom situation sorted out and we'll be in a better classroom again. And hopefully by then, we may even have some Wi-Fi. I will try to keep you as posted as possible. Just in terms of some logistics, you do have an assignment coming up, which is the check-in number 1. I did send out, I think it was last week, an invitation to sign up to GradeScope. If you didn't get that, please reach out to me because I know I haven't used GradeScope with you guys specifically in this course. I have been using it in my lab courses, in my SAM and ARM course. But if you didn't get that invitation, let me know and I'll send it again because I'd like you to be uploading your assignment to GradeScope. For those of you who used it last year, there's a new improvement that I think you'll like. There is an app that I encourage you to download. So download the GradeScope app, and then when you go to submit your assignment, you just open the app, and the app has a built-in screenshot. Okay, so you don't need to be using a different platform to take a picture of your assignment and then upload it. You can do it all within GradeScope. And one student asked me about the assignment, and I made a little video for them to help. I'll let other people ask me, and if you're interested, I could send you that video as well. Just some clues or suggestions. For those that had a chance to look at the Chem Activity 5 tutorial, I appreciate that. I would suggest that looking at it once isn't going to be enough. But that said, today's lesson will put it all into context, I hope. I am still, however, at Chem Activity 3. There's a few things that we need to finish off with. And so here I'm showing you this summary chart, which is at the end of Chem Activity 3, and we've gone through a few times. Yes, on page 25. So if we can just digest this for a second, this is our toolbox of different reactions that allow us to change benzene in a number of ways. And essentially, these are almost all of the reactions. So what's going to happen going forward is we're going to see what will happen once you put a substituent on benzene, and how do you put a second one on? Where is it going to go? So I'm not going to introduce any more reactions. These are enough, but you'll be making use of them, and you need to understand what they do, what their limitations are, and that sort of thing. So in the interest of a little bit of practice, I am now looking on page 21 of your course pack, and I see this particular question right here. And it says, show the reagents required and write the complete mechanism for the following transformation. Well, transformations, because there is another one below. So I'm going to pause here for a second. If you haven't done this, I'm going to ask you to consider it right now. And it's to, in a sense, help you recall what we've been looking at. And I point out to you that what we have added in this particular case is this carbon chain. But it's a carbon chain that's bigger than 2 carbons. Therefore, we will need to do an acylation. And the particular reagent in question, so I'm kind of helping us out here a little bit, would be this 1, 2, 3, 4 carbon thing, but there'll be a carbonyl onto which the benzene will be reacting, and then that would be, for instance, the chloro group. We would need aluminum chloride or iron 3 chloride. So that's the way to be thinking about it, that you're attaching to that, that carbon that I just highlighted in red. That would be step 1. But of course, we don't just want to add the carbonyl. We want to end up with an alkyl chain. So we will need to do a reduction, and that's the Clemmensen reduction. And Clemmensen reduction doesn't start with an N. That is, we need zinc, mercury alloy, but we'll just do this for now. So those are the reagents necessary. Depending on your comfort level, if you're wanting to prepare the electrophile that will react, you can form the complex with the aluminum and things, but ultimately what you're going to need is this 1, 2, 3, that carbon there, and that's going to be attached to our oxygen as a triple bond generally. That would be the resonance form that would be the contributes the most. So you can jump right to that if you're comfortable, or you may need to form the Lewis acid complex and show how it gets to there. So I'm starting at that spot, or at least together we've got to this spot, and I ask you to take a minute and just see if you can run through the mechanism. I didn't ask for all the sigma complexes, so you don't need to draw all the sigma complexes. Or that is all the resonance forms in the sigma complex. And remember that you don't need a mechanism for the Clemmensen reduction. So I'm just trying to get your brains to be thinking about this again. I'll pause here. Maybe I can even walk around and take a look, see how you're doing. But all the carbons on the benzene ring are equal, so it doesn't really matter where you have them attached. I know the oxygen, no. The oxygen's tempting because it's positively charged. But remember that the new bond is being made to the carbon. This is a whole week ago that we were looking at this, so I'm getting more fresh in mind. That's great. And that one, otherwise, you're going to have too many bonds on the carbon. I see what you're doing. And that would be okay, except the positive charge then should be on that carbon right there. There is not an extra carbon. Okay. Right? So it's okay to use the less common resonance form with the carbocation. come back here. So the attack happens on that carbon right there, not here. Because if we see what gets joined, right? If I may borrow your pen a second. That carbon right there is that carbon right there. And you still have the Y shape at the end. Yeah. Oh, okay. So, it'd be helpful to look at an example, but what happens here is that hydrogen is getting replaced, and so your Lewis acid is going to pull off that hydrogen, and then a new bond will be made there. Okay. Yeah, so the attack's there, and then the bond breaks. So what I'll do is, I mean, you guys have had time to be thinking about it, and if you're not completely done, what I'm going to do is move forward. I wonder if I can get my mouse to be working here. It'll be easier. Help me move forward. Let's see. Oh yeah, look at that. Just move this over a bit. Okay, so here I have the example of the mechanism. So you may want to be checking. And you can see that really the mechanism is just these two steps. Understand it, and this is kind of talking to or addressing what Aiden did. He had his carbocation here, and then just a double bond, which is totally fine. But make sure that it's that carbon that gets attacked. And again, you could have done the reaction here or the reaction there. It's all the same. We form this intermediate, high energy intermediate. And essentially the hydrogen gets removed and the pi bond recreated. Aromaticity is regenerated, and then there's the Clemmensen reduction. Normally I would have either a comma or a dash there. And that's what happens. So I'd like you to be able to do this at multiple levels. One, just to be able to predict the reagents, predict the outcome, but also to write that mechanism. And then today especially, we're going to be working with the sigma complex. Any questions about that first example? Okay, in part, I go over that because I need to present to you something a little different. And I want you to see the differences and the similarities in this example. So rather than jump to the part B, I'm going to go back to page 20 and talk about this. So just back to page 20. And I'm talking about, and I say one important limitation to the Friedel-Crafts acylation. So Friedel-Crafts acylation have fewer limitations compared to the alkylation. Recall that the alkylation results in possible multiple additions, can't be done with a electron withdrawing group, and you get rearrangements. Acylations can't be done with electron withdrawing groups, but you don't get rearrangements, you don't get multiple acylations, but here is one limitation. And I have tried to pick or limit the scope of the reactions. As you're looking through them, you may disagree. You may say, oh my God, there's so many of them. Honestly, there could be way more, but I did include this one. This one's called the Gatterman-Koch reaction, and it's the issue that apparently we can't, if we want to put just one carbon acyl group on, in other words, to form the benzaldehyde, we can't use what you might have expected to use, this methanoyl chloride, which is shown there, and then I show the X. For whatever reason, I haven't gone deep enough into the literature to find out why this reaction doesn't work, but apparently you can't do it. You can't use that methanoyl chloride. So you have to use an alternative approach. And actually there's some close similarities to the alternative approach. So the Gatterman-Koch reaction uses carbon monoxide, so that would be a gas, under acid conditions. So essentially you would bubble carbon monoxide gas into an HCl solution. And if you take a look at the electrophile that forms. And so I'm showing this setup here. I show initially the Lewis structure, or at least a semi-Lewis structure for carbon monoxide. And under acid conditions, the carbon gets protonated and we form this intermediate. Hopefully that looks a lot like the acyl intermediate electrophile that's used for the acylations. And so once again, we have the attack of the benzene, we form the sigma complex intermediate, and there's not a whole lot of stuff around. So, you know, and I said an HCl solution, actually it's probably an inert solvent. So I'm going to pick on the chloride as being the base that removes that proton, even though it's a very poor base. There's not much else around. Hopefully you see the similarities in the mechanism. So that's the Gatterman-Koch reaction. I don't know what you need to do. Oh, and by the way, sorry, that was on the next page, page 21, top page 21. I don't know what you need to do to remind yourself about this. This is often now forgotten, like you see it. So if you put a little star or a little asterisk or something to mark the page, right? Because you will see this again. And rather than just leave it, let's try the reaction. Here we go. So now this is part B on page 21. Show the reagents and write the complete mechanism. And again, hopefully this starting to feel quite familiar. So I'm going to pause once again, opportunity for you to practice writing this mechanism. Again, if you wanted to start directly with the electrophile, you don't need to show how it forms, but in some way, figuring out how it forms helps you remember what it is. And maybe this helps also reinforce the acylation reaction, what that electrophile is. And it reminds you that the positive charge in the sigma complex is not where the substituent has gone. The thing that gets added, it's always on the adjacent carbon. There's always a sp3 hybridized carbon and the H needs to be removed. So here I have the mechanism. This is reminding me that after today's lesson, I'll be posting a short quiz in active chem, and some of these things are reviewed in terms of the nature of the sigma complex. I don't know if this is being picked up in the recording, but we have a lovely pipe sound that I've put in at least 3 work requests.
That's good.
Yes, you can see that it hasn't led to it being fixed yet. So I just want to make sure that people have had enough time. And let's see, in this case, right, didn't have the Clemenson reduction because I actually wanted to do the acylation. I'm not so sure that this would, how do I put this? That if you just wanted to put a methyl group on, I wouldn't do this. If you wanted to just put a methyl group on, I would just do an alkylation. I wouldn't do this and then do a Clemmensen reduction. Except, you're going to see down the road, sometimes we do want to actually put this on first because it influences how the benzene ring reacts. And then we might want to do the Clemmensen reduction. More about that to come. Have you had enough time then? I would like to do one last question concerning Chem Activity 3. Okay, that's this then. So this is a check your understanding question. Oh, and actually, maybe what we should do is just for completeness, this is the summary chart that we've been working from. And this is the one that's on page 25. What I might do is to fill in a few more details. And so again, mine's a fresh summary chart. So I need the copper chloride here if I'm using iodide. This is either tin or iron under acid conditions. And then we saw one other thing now in terms of acylation, the Gatterman-Koch. So this may be a place where if you add it here, then it reminds you, oh yeah, there's this Gatterman-Koch reaction. And what it involves is, of course, carbon monoxide, HCl. And this is if you want to make, for instance, the following. Okay, so if you just want to add that one carbonyl carbon group, then you need to use the Gatterman-Koch reaction. I find it helpful to have a summary chart against which I can compare. So just adding to that. Okay, so here's the question I'd like to ask before we leave all of this. And it's one of the check your understanding questions from this activity. It's found on page 22. I would have opened this up in Active Chem, but instead, at least for the purpose of people being here, what this question is asking is, which one of these will not produce isopropylbenzene? So we can do 1, 2, 3, 4. And what I'm getting at here is we're starting with benzene, and what I want to do is make this. So I just want to put this isopropyl group onto the benzene. Which one of these reactions will not give isopropyl benzene as the major product? So take a minute, consider, and then for the people that are here, I may try to get you to commit a finger or a set of fingers. Okay, so maybe I can see what people might be thinking. You have an idea here. Got 2 chloropropane, 1 chloropropane, propanoyl chloride. Maybe what I should do is just remind you that propanoyl chloride looks like the following. And again, I'm not assessing you on the nomenclature here. The propanoyl chloride would look like that, 3-carbon acyl group, or 1 propene would look like this, of course. So which one? What do you guys think? Okay, I see a hand for fingers for Megan. It's okay to be wrong. Guess it's one of them. Okay. Okay. We do this, we're not sure, right? Okay. All right. So the correct answer is 3. And so this will not produce isopropyl chloride because what it's going to produce is propyl, I said isopropyl chloride, isopropylbenzene. This will produce propylbenzene, right? There will be no rearrangements. The whole issue is about this idea of rearrangements. So if you start with this guy, 1-chloropropane, and maybe I should just draw it out, you might think that the product should be propylbenzene, but it won't be. Remember that any time that you have an alkyl halide that's longer than 2 carbons, you're going to get rearrangements. So treatment 1, treatment 2, and we'll talk about it in a minute, treatment 4 will all produce isopropylbenzene. Only treatment 3 will produce the propylbenzene. And just to highlight what will be the outcome here will be this. Now, what about this number 4? And, you know, like I'm trying to limit the number of reactions, but you may recall that if you treat an alkene under acid conditions, and so for instance, if I'm not so worried about that it's sulfuric acid, let's just say you treat it with the hydronium ion, and if I draw the hydronium ion, for instance, like this, so well, what does this pi bond as a nucleophile do? Well, we've seen that it can pick up a proton. And if it picks up a proton, we'll end up with a carbocation. And the carbocation will be in that more substituted carbon. So that would be another way of actually doing a kind of alkylation. And you know, it'd have to be on that more substituted carbon. So I just wanted to point that out. Hopefully, actually, that will be relevant to you a little bit later on. So this finally ends the chem activity 3 and brings us to the chem activity 5, because chem activity 4 was about nomenclature, and to the whole joy of the chem activity 5 tutorial. Now, I created the tutorial to provide some background for what we're about to discuss. And so I'm hoping that the tutorial and what's in the course pack go nicely hand in hand. Going forward, I intend to kind of combine the two, but for now they're sort of existing separate. And I don't know, maybe that's actually not such a bad idea. One of the reasons why I gave the handout is I want to refer to specific diagrams that are in the tutorial. So that's why you've got that diagram or that page with diagram. Also, I printed out another copy of page 29. Long story, I made really short. I'm in the process, or was in the process, of redoing Chem Activity 5. Somehow, I can't remember why, the course pack didn't get the most updated version of these diagrams. The most updated version of the diagrams, instead of referring to Z and X, as is showing on the top of page 29, I wanted to actually have the words electron donating group, electron withdrawing group. So this is why I printed off that first page again, and that's what you see in this diagram. But you know, if you want to call them Z and X, that's fine. But I think it's more descriptive as electron donating group, electron withdrawing group. Next, for various reasons, I've changed my symbol for the electrophile to be A instead of E. So in my slides, you will see A. In the printout for page 29, you'll see A. But in the rest of the course pack, Chem Activity 5, you'll see E. Understand that E is the same as A in terms of it's the electrophile. Next year's course pack will have all that updated. The other handout, of course, contains excerpts from the tutorial. Okay, with that little bit of introduction, let us begin. If I could, for those that are here, if I could get you to look at the screen, and I'd like you to be thinking, okay, you have benzene, and we said, okay, in order to get benzene to react, we need to present to it a better electrophile than normal. So it's not just like the regular pi bonds reacting. HCl is not good enough. Br2 is not good enough. It has to be this electrophile that's with a Lewis acid catalyst. So that's one way to get benzene to react. As it turns out, once benzene has a substituent, its reactivity changes. And it's all about how that substituent affects the sigma complex. All the action is happening there. And it all has to do with this idea of the Hammond postulate. So actually, maybe what I'm going to do is just jump right to here, and I'll come back to that previous slide in a second. So this is on your diagram. This was in the tutorial. This is slide 4 of the tutorial. If you have benzene alone reacting, that's corresponding to the black line. And benzene will react at a certain rate according to its activation energy. And so really what's important is the energy at the transition state. But as I've mentioned before, it's hard to know exactly what that transition state looks like. So what we do instead is we focus on the intermediate. And we say, well, how stable is that intermediate? That reflects how much energy that transition state has or is required in order for the reaction to proceed. For benzene alone, you just have those 3 resonance forms, and there is no particular extra stabilization. It's just those 3 resonance forms. And so that's, in a sense, a point of reference. But if we already have a substituent on the benzene, we can look at that sigma complex and say, does that substituent improve the stability of that positive charge or take away from the stability? There are 2 possibilities. The substituent is either an electron with group or overall an electron donating group. Those are the 2 situations. So EWG means electron withdrawing, EDG means electron donating. Now, we've kind of talked about the stability of charges before, but our focus was on negative charges. You need to flip your thinking here. This is all about the stability of a positive charge, something that's electron deficient. So hopefully it makes sense to you that if you have a group that's mainly electron withdrawing, it sucks electrons out of the ring. That's going to destabilize that positive charge even more. Therefore, it makes the activation energy for that reaction higher. It slows down that reaction. That's the line in red. Okay? So, I mean, it's as simple as that. Electron withdrawing groups are going to slow down the reaction. Electron donating groups help mitigate the fact that you have a positive charge. Electron donating groups will donate electron density into the ring, thereby lowering the activation energy compared to that of benzene. That reaction will occur more quickly. So that's the crux of it. Essentially what your challenge will be is to decide what those substituents are. And I believe you have enough background chemistry to not have to memorize what these groups are, but actually see, interpret them, read them, if you will. I'm sorry, I'm trying to get my mouse back. Hello, mouse. Come on. There we go. Okay, so I'm just coming back to this diagram then. So we have either an electron donating group or an electron withdrawing group. And maybe what we can do at this top part of the diagram is if we talk about relative rate of reaction, I hope it now makes sense to you that you'd expect that if you have an electron donating group on your benzene, the rate of that reaction would be faster than benzene alone. And benzene's reaction would be faster than if you have an electron withdrawing group. And it's all about the sigma complex. So in your explanations, I'm going to be wanting to see the words sigma complex. I'm going to be wanting to see the words stabilization or destabilization. I'm going to be wanting to see the words higher activation energy, lower activation energy. And then after that, it's like, yeah, it's super easy. Now, there's something else, though, and you're going to see that in this particular case, so I'm showing this sort of generic. You've got either an EDG or an EWG. Benzene reacts with the electrophile. In this case, you can see that I've arbitrarily put the electrophile in the ortho spot. When you put the electrophile in the ortho spot, this dictates where that positive charge is going to be. So we can draw two resonance forms where you can see the positive charge is here and here. But inevitably, there will be at least one resonance form, or at least one resonance form that's contributing to the overall resonance structure, where the positive charge is going to sit right below that substituent. So when you have an ortho substitution, it's greatly impacted by that substituent. If the substituent's electron donating, that's a good thing. It's going to speed up that ortho reaction. If it's electron withdrawing, that ortho reaction is going to be particularly affected and will be particularly slowed down. So again, it's always going to be about the focus about what's going on with that sigma complex. That's the preamble. That's the background. Do you have any particular questions at this stage? Don't worry if it's not right now. It can come later. Sorry, I should have brought some water. But we're in the lab. I shouldn't be drinking water. Anyways, here we go. So I have talked about this diagram. We're going to be referring a lot to this diagram. It's an energy coordination diagram. And I believe that this is really, in combination with looking at the sigma complexes, looking at these diagrams really help you understand how the substituents have their effect. Not all textbooks take this approach. I believe it's a really strong approach, and that's why I produced that tutorial. So let's go. On the the rest of page 29 now introduces all the different types of substituents. And they're divided up into 6 main classes. So you have 3 activators. You have 3 sets of deactivators. They're also divided up into 2 main groups, ortho-para-directing and meta-directing. When we say ortho-para-directing, that means when that substituent is there, it speeds up the reaction in the ortho-para direction. How does it speed it up? It lowers the activation energy, or offers an alternative pathway of lower activation energy when there's the ortho-para substitution. Meta-directing, those groups, the activation energy is less than the ortho-para, and therefore that reaction's faster in that orientation. Let's take a look at the different types of groups. Hopefully you can start to pick out what the groups, what the atom connections have in common if they're in the strongly activating category, or if they're in the moderately activating category, or if they're weakly activating, etc. For instance, if you look at the weakly deactivating, hopefully it's clear to you they're all halogens, right? So the halogens are all weakly deactivating. Done. What do you notice about the strongly activating? What do they seem to have all in common? What atoms are in, oh, and maybe one of the things that I should point out to you is, I'm going to put a little X here. This is where the group is attached to the benzene. Okay, so it's that group. So just maybe to clarify, this would represent the following. For instance, it would be, well, the simplest would be anisole, for instance. So if you had that, okay, that would be represented by that group. Did you notice anything about those activators? What do they have in common?
They all have lone pairs.
Again, please?
They all have lone pairs.
Okay, nice. So they all have lone pairs, but what distinguishes them, for instance, from the weakly deactivating, which also have all have lone pairs?
So,
It SP2. Not as drawn, but yes, they're all going to be SP2 hybridized. What atoms are involved? This is actually important. Yes, that's not trivial. Nitrogen and oxygens. Yes, and you know that those are pretty common moieties in organic chemistry. So yeah, I like what Ariel said. Lone pairs. Yeah, they're all going to have lone pairs. And they're all nitrogen and oxygen. That's actually relevant because you can see that the halogens, yes, they have lone pairs, and that'll be important too, but they're not nitrogen or oxygen. So we're going to go through this more carefully, unpacking what these are, but hopefully you're starting to see, yeah, there's some commonalities. Anything you notice about, for instance, the moderately deactivating? And again, remember that they're right but against the benzene ring. So what do you see that all of these guys have in common?
Not bonded directly to the oxygen, but there's an oxygen really near.
Okay, there's an oxygen really near. This is true. And what sort of bond to that oxygen? A double bond, yeah. So okay, so if you look at that last example, it's a carbon, it's not bonded to an oxygen, but it's a pi bond to, and what it's going to be is, instead of it having to be an oxygen, an electronegative atom. Okay, and moderately deactivating, that means less reactive. What we're going to see is they're all electron withdrawing. So let me put some summary comments, and I think I might have to erase. Oh no, okay, we're fine. Okay, so if something is activating, it means that its reaction is faster than that of benzene, which means that it has to be overall electron donating. So what do these guys do? Well, I'm going to put some notes here. The first two groups, how they are overall electron donating is they donate by resonance. So I ask you to put these little things on the side there. They all donate by resonance. You're going to see that the weakly activating donate by hyperconjugation and in some cases resonance. You're going to see that the halogens donate by resonance. And then moderately deactivating, so these are going to be the electron withdrawing guys. And they mainly withdraw by resonance. And then the strongly deactivating, you're going to see that essentially it's the result of this kind of hyperinduction, like it's really electron withdrawing because of induction or resonance. And I'll go through each of these to show you how this works. But one of the things that I'd like to point out before we go on is when we're saying that these guys donate or withdraw, we're saying this relative to the benzene itself and the substituent, if you will, that's already on benzene, which is a hydrogen. So it's always comparing against that hydrogen. So one of the things that will be true about comparing against that hydrogen is essentially all substituents except the alkyl groups are electron withdrawing by induction. So I'm going to add this to the side here. And this is mentioned in the tutorial. All groups electron withdrawing by induction except for the alkyl groups. And that's these guys here. So kind of the baseline, comparing just benzene itself, any substituent that's common, they all involve atoms that are more electronegative than hydrogen or carbon. And why I say carbon is, it's the carbon that's in the benzene there. So all these other groups, nitrogen, oxygen, fluorine, chlorine, bromine, you put sulfur on, you put any other group besides that carbon, it's more electron withdrawing. So all groups withdraw by induction to some degree. So you might expect actually all of those groups would simply be electron withdrawing. But the issue is that those things that I've highlighted in green there is all of those groups and the ortho-para directors, the strongly activating, moderately activating, weakly deactivating, they all somewhat counterbalance the fact that all groups, except the alkyl groups, are electron withdrawing by induction because they can donate by some fashion. And usually the means by which they can donate is resonance. So it's always this kind of fight between to what degree can something donate by resonance and to what degree are they withdrawing by induction. So in some ways, this section of the course becomes a little more complicated in that it's not just monovariant. It's not just one factor you need to consider. You have to look at this balance. To what degree can something donate by resonance? To what degree is it pulling electron density away by induction? And you might say, well, how can I possibly know? Well, the thing is, if something is activating, and I think this is probably an important sentence, if something is activating, the donation wins. If something is overall activating, it is overall an electron donating group. So I show this in this context. It may be worth us now coming back here in this more general diagram. And in terms of what about this electron donating group? An electron donating group is not something that only donates. We now know that all groups withdraw to some degree by induction. But we say that something is overall an electron donating group because its ability to donate outweighs any ability to withdraw. And the way that it can win donating is by resonance. So maybe one of the ways to put this is overall electron donating. And perhaps we can put something like this. Resonance beats induction. Because remember, what's going to happen with induction is electron withdrawal. Actually, maybe we could put electron donation by resonance beats electron withdrawal by induction. In terms of electron withdrawing group, it's just there's induction and then there's usually something else. So overall electron withdrawing, but that's pretty much the only thing that's happening, electron withdrawing. So again, everything's electron withdrawing except for the alkyl groups, but something is overall electron donating if the resonance can beat the induction. hopefully I haven't lost you completely. Hopefully some of the things that you've seen in the tutorial might start to make a little more sense. How are we for time? Okay, yeah, we've got about a half hour. So let us proceed. I just want to stop here with this diagram though. Over time, as we start to work with this, and I'll go through these each class and try to help you pick out what the important features are. But yes, you need to know these guys. No, unfortunately, you don't get this as a cheat sheet. Right? So you need to recognize these guys. But I'm really hoping in the end, it's not just a matter of memorization. It's a matter of recognizing their characteristics. I do have this diagram, which is on page 30. And what it's showing you here is just kind of the breakdown. That, again, we have two main groups. We have the activators, we have the deactivators. All relative to benzene, if you will. So the anchor point here is relative to benzene. In terms of activators, we have strong, moderate, and weak. And yes, I need you to be able to distinguish what a strong is, what a moderate is, what a weak is. We need to know each of these different ones. And it's not, as you will see, it's not that hard. I need you to know who the weak deactivators are. But one of the things that you're going to notice is all four of those things that I've just said, they are orthopara-directors. And so I need to also explain, well, what does that mean? And why are they orthopara-directors? But understand, we can say the following. All activators are orthopara-directors. But not all orthopara-directors are activators. I'll say that again. All activators are orthopara-directors. But not all orthopara-directors are activators, because you can see that the weak deactivators are also orthopara-directing, and I have to show you why that's the case. We can say all meta-directors are deactivators. Now, you do not need to distinguish between moderate and strong. I just need you to know they're deactivators. And in part, when you look at the list and you look at different textbooks, you'll see sometimes textbooks will put what I'm putting as moderate, they'll put it as strong, and vice versa. So I don't need you to distinguish between those. I just need you to know that they're deactivators. Okay, so just one class is fine, because they all do essentially the same thing. All right, so let's get into this first example of trying to understand why strong and moderate activators direct orthopara. We're going to do this from two different perspectives. One, from looking at the sigma complex of the intermediate, and second, we'll look at those reaction coordination diagrams. I'm using the example of anisole in this case, but it could be any strong or moderate activator would work. Any one of those would work in this example. You're going to see, if you look at future midterms, like practice midterms, or if you look at a future exam, often there'll be a question kind of like this, where it's set up, but the diagram isn't complete. I just sort of scaffold all the rings in there, and you need to put in the details. So let's kind of unpack what's going on. In each case, I'm thinking about the reaction of the substituted benzene with our electrophile. Okay, so there'd be that, and in this case, it would have to be that so-called bottom pi bond. So we form the intermediate. I'm looking at what happens when you have an ortho substitution, when you have a meta substitution, when you have a para substitution. And in each case, of course, all of them have the three typical resonance forms that contribute to the resonance hybrid. If you look at the ortho-para substitution, however, you will notice that through using curved arrow notation, I have drawn a fourth resonance form. And understand that like the way I'm showing the progress here is I draw this first resonance form, and then I recognize that as an allelic carbocation, so I can draw another resonance form that puts positive charge there, and then another one, and then I use that third resonance form to discover this one. But you could get to that fourth resonance form just from right here. Like, there are various ways to find those four resonance forms. So in a similar way, I found a fourth resonance form for the para. Is there a fourth reasonably contributing resonance form for the meta substitution? Well, let's explore. So I'm going to do this kind of thing. I'm going to do the same kind of thing that I did with the orthopara. So I'm going to say, okay, what if the electron density is delocalized, and I'm trying to find a fourth resonance form? And as I'm doing this, you can see, oh, okay, yeah, I can put a positive charge on that oxygen. I put a pi bond there. And, oh, the negative charge is here. Compared to the other three resonance form, is this resonance form that I just drew, is this going to contribute much? And the answer is no. I've just introduced further formal charges. It doesn't help stabilize that positive charge. So the point being is, in a meta substitution, there is not a fourth resonance form that helps stabilize that sigma complex. Now, the next question I'd like us to consider is, to what degree does the fourth resonance form in each of these cases contribute to the overall resonance form? Is it about equal to the other three? Does it contribute less? Does it contribute more? Based on what you know about how resonance forms contribute to a resonance hybrid, what do you notice about that fourth resonance form?
Positive charges on oxygen.
Yes, so on a highly electronegative atom, okay, we think about that. So maybe it contributes less. But there's another thing we should consider. They all have octet. That fourth resonance form is the most highly contributing. So in the ortho and para pathways, are you going to expect the activation energy to be higher than or lower than, one, the meta pathway and benzene itself? It's going to be lower. The activation energy for the ortho and para pathways will be lower than the meta pathway and benzene itself, because the sigma complex is, I'll say, highly stabilized, or more highly stabilized. Okay, I'm going to put this into wording. This is the kind of explanation that I would hope someone would give to justify. The ortho-para substitution results in an additional fourth resonance form. But not only that, it's the only structure that has a complete octet, so it's highly contributing. Right? So the point being, fourth resonance form, highly contributing. And then make reference to the sigma complex. How does that affect the sigma complex? It stabilizes it relative to benzene and relative to the meta pathway. How does that impact the activation energy? It's lower. And then by, if you really want to go on, you could say, well, then that reaction's faster. But I think just by saying the activation energy is lower, you're essentially there. What I think is powerful about this section of the course is it allows us to apply our knowledge, previous knowledge about resonance forms, about formal charges, and offer, I think, a solid explanation for why something happens. And even if you don't go on to be organic chemists, this skill in being able to compile evidence and provide a compelling argument is a useful skill. I can come back to this diagram if you need more time, but I just want to now quickly jump to this slide 9. I think collectively, both the sigma complex diagram and the slide 9 from the tutorial really help us understand what's going on. Now, in slide 9 in the tutorial, instead of using anisole, I used the amino group, which I hope you recognize is a group, nitrogen or oxygen, that has that lone pair of electrons. And note, I'm comparing not all 3 substitutions, but just the ortho substitution and the meta substitution. The para would behave like the ortho. Look at the activation energy for the ortho substitution. It's less than the meta, and it's less than that of benzene. Therefore, we would say that the amino group is activating in the ortho-para direction, because that group is overall electron donating. And how is it electron donating? Well, let's come back and take a look. How ultimately did that oxygen donate its electrons? The 4th resonance form, by resonance. Because what's also going on in the background is this oxygen is always pulling electron density away by induction. It's always doing that. That's happening. But it's been counterbalanced in a really solid way by the fact that there's resonance. So one of the things that you may also notice is, look at in the meta direction then. So you've got this oxygen there. It's pulling electron density away by induction. How would you expect the sigma complex in the meta direction compared to that of benzene alone? Good. Well, higher activation energy, less stable. Okay, benzene alone has those 3 resonance forms, but it doesn't have an oxygen that's sucking electrons away by induction. So when we say something is electron donating, we don't mean necessarily for all substitutions. When we say something is activating, it's not activating in all directions. Let's look at this diagram again. I think this diagram really helps us see that the meta pathway is actually deactivating. The activation energy is higher for the meta pathway. Why? Because of induction. So in combination, those sigma plot diagrams and this energy coordination allows you to see what's going on. Many textbooks just show the sigma diagram, and it's a little hard to really, I think, pick out, okay, right, it's just the ortho-para pathways that are activated. And, we only need to go through a couple of these examples because this applies to all strongly activating and even the moderately activating. It's just the moderate doesn't do it quite as well. Any questions so far about this diagram? Okay, let's go on. I'd like to hopefully run through both the like the strongly moderate, the weakly activating, and the deactivating. And that would be a good place to stop today. So let us move now. Oh yes, what I do at this point though, before we get to the weakly activating, let's think a little bit about those moderate activators. So maybe if I just come back here for a second, let's look at the group. Remember how you recognize that the strongly activating all have nitrogen and oxygen with lone pair of electrons. Well, the moderately activating also have nitrogen and oxygen with lone pair of electrons. But notice that they all have right next to them a carbonyl group. Right? So there's a feature there. It's kind of like facial recognition. It's like, can you recognize your friends? Can you recognize your enemies? You can recognize this group. That's its characteristic. So these groups are donating by resonance. That's what I'm trying to show in this diagram right here. And do I actually have? I think I write it down too. No, I don't. So let's just say electron donating by resonance. And I just picked one of the sigma resonance forms at the sigma complex in the ortho substitution. Just say it's electron donating. But because in each of these cases the oxygen or the nitrogen is beside a carbon that's making a double bond to an oxygen, it's an example of an allelic lone pair, but in the opposite direction. So to some degree, the electrons are not being completely donated towards the sigma complex. And so we can draw this additional resonance form where it shows, well, yeah, those electrons are actually also being back donated, if you will. They're not fully committed to the sigma complex. What am I doing? Sorry, come back. In my mind, it's a little bit like thinking about psychology, although the psychology profs would shudder when I say that. But you're interpreting the situation. What's the behavior of that group? Oh yeah, that group, they're generous, but yeah, no, they not completely. They're not completely committed. If you can think of them that way, that's why they're only moderately activated. Although please don't put that as just as the explanation. They're not completely committed. No, you should say that there is this resonance involving the carbonyl that doesn't allow those electrons to be completely donated. And here, I forgot a carbon. Okay, so then let's look at the moderate activators. I said moderate activators. Let's look at the weak activators. You'll recall that the weak activators are essentially the alkyl groups. And I want to pick right now on just a plain old alkyl chain. Just carbon chain. It could be a methyl group, it could be an ethyl group, it could be an isopropyl group. So let's imagine that there's this reaction of benzene. We form this sigma complex intermediate. Yes? Let me see. Yeah, I was probably not paying attention. Let me see. It has to be, you're right. I mean, to be honest, technically it doesn't matter, right? Because they're all delocalized. But if I want to be kind of consistent with how I'm drawing these things, yes, I should have done that. Thank you. And for instance, if on a midterm you pick any of those pi bonds, so-called pi bonds, that'd be fine too. But yeah, I prefer to be consistent with where that positive charge shows up. Yeah, thank you. Note that this time I didn't draw a fourth resonance form for any of them because there isn't a fourth resonance form. The alkyl groups do not donate electron density by resonance. There's no lone pair. There's no allelic lone pair. In the past, we know that an alkyl group can stabilize a positive charge. Remember, secondary and tertiary carbocations are more stable than a primary. By what mechanism are these alkyl groups stabilizing the positive charge? Hyperconjugation, stabilization by induction. The hyperconjugation is more important. So we know alkyl groups stabilize by hyperconjugation and induction. Now, this is one of the rare cases where the substituent isn't pulling away electron density by induction, so that's not happening. So if all of them are in a sense actually donating by induction, right? So I don't want to. I'm not going to do it for all the diagram, all the different structures, but you know the background here is this alkyl group is actually to some degree donating by induction in all cases. Even though it's a carbon-carbon, the ring is electron deficient. So why would it be that the alkyl groups are ortho-para-directing? What's so special about the ortho-para pathways compared to the meta pathways when by default the alkyl groups are already donating by induction? There's something unique about the ortho-para pathways.
The positive charge goes on the tertiary.
Nice. And remember how at the very beginning, the ortho-para pathways are always more affected by the substituent because there's always going to be a resonance form where the positive charge will sit right below. And it's only at that resonance form that you can have hyperconjugation. Hyperconjugation requires that leaning in of the bonds that are in the sigma bonds into that so-called empty p orbital. And so to put this in words, for instance, ortho-para substitution results in one resonance form contributing more significantly due to stabilization by hyperconjugation. And so, yeah, they only have 3 resonance forms, but one of those resonance forms is more stabilized than any typical resonance form of benzene alone and that of the meta pathway. So again, the activation energy is lowered, not because of resonance, but because one of the resonance forms has that additional stabilization by hyperconjugation. Actually, that's a very good arrow. Let's try that. As you're writing this down, I'd like you to be reflecting then. What should the activation energies look like compared to benzene? Well, we know the ortho-para pathway will be less. What about the meta pathway? Would the meta pathway's activation energy be greater or less than that of benzene? Make an argument. Why do you think greater, Aiden? How does this sigma complex compare to that of just benzene alone? It's actually more stable than that of benzene alone. Not much, because it's just induction. Right? So both pathways are actually faster than benzene alone, but these are the fastest. Right? So what does our diagram look like? Now maybe when you go back, if you go back to the tutorial, you say, oh yeah, right. That's why both of these lines for both pathways, meta and ortho, para as well, the activation energy is less than that of benzene. It wouldn't be as low as the strong activators, because this is just hyperconjugation, but it's less than that of benzene. The meta pathway is also less than that. So overall, actually, the alkyl groups are activators, and they're also overall electron donating. But they're especially donating for the ortho-para pathways. We have actually have 7 minutes left. So that allows us to, because I want you to at least have been exposed to what happens with deactivators. Any questions about the weakly activating? Okay, so then the last major category are the moderate to strong deactivators. And again, I'm not asking you to distinguish between them. You can see that it's not that hard to distinguish between the strong, the moderately strong, and the weakly activating. And we'll look at the weakly deactivators on Wednesday. And I don't need you to distinguish between the moderate and the strong deactivators. And they do the same thing. So now let's look at our diagram here. I picked the cationic ammonium ion, but it could be any. It could be the nitro group. The nitro is a really good example of the strong. Oh, that's a pretty bad arrow. By the way, did I do the meta incorrectly then the first time?
Yep.
Why don't you speak up then?
I was going to, but then you turned the page.
I'm teasing. Okay. So to be more consistent, it would be better to do that. But again, given the true understanding of those pi systems, it doesn't really matter. Okay. Thank you. So now back to where we were. So here are our three sets of substitutions. Note there isn't this fourth resonance form to worry about. Recall that only those things with lone pairs of electrons can donate electron density by resonance. So resonance is not an issue in terms of donation. Strongly and moderately deactivators can withdraw by resonance, but that won't create a fourth resonance form in the sigma complex. So let's look at what's happening here. These guys are meta-directors. I'll also point out that these groups, they withdraw by induction, as all groups do except for the alkyl groups. So they're all withdrawing by induction. So there's this destabilization of the sigma complex because electron density is being pulled away. So that in part explains why these are deactivators. But why would this go meta? What's so good about the meta?
Because the one has the positive exactly opposite.
Go.
Like the positive on the unknown is opposite from the positive.
So you're talking about in the ortho and the para? Are you looking at the completely opposite? Okay, all right, I get it. Yeah. So what Brooke is saying is, note that the positive charge looks like it's the furthest away in the meta, and that's interesting actually that you mentioned that, because that is true. So I guess one could argue that resonance form is the least destabilized. Yeah. I've never actually seen that argument presented, but I would buy that as part of a larger argument. Okay. Generally, I think of those three resonance form as essentially all equally contributing and not particularly great. So I said, what's so good about the meta? Maybe we could ask this question differently. What's so bad about the orthopara? Not so hyperconjugation, it actually refers to donation of electron density into a so-called empty p orbital.
It's the opposite.
Yeah, but there is no such thing as the opposite, right? But that's interesting. Again, that's something I've never thought of. Is there actually something the opposite of hyperconjugation? I would just rather refer to this as induction or hyper electron withdrawal by induction. Right? So notice, again, orthopara substitutions are always more affected by the substituent. So I think we can make an argument that resonance form and this resonance form are particularly affected by that substituent. So they are particularly destabilized. So I'm not sure, although I don't want to completely dispute what Brooke said, that the meta pathway it isn't to any degree particularly stabilized, but it's not as destabilized. So the meta pathway is the best pathway to choose given that they're all bad. It's the best of the worst, if you will. Right? So here's how I might put it in some wording. Oh, pardon me. Only the meta substitution avoids the enhanced destabilization. And in a sense, another way of thinking about it is, if we think about really which resonance forms are contributing to help stabilize the sigma complex in the ortho-para pathway, really there are only two that are reasonably stabilizing, because that third is particularly destabilized by having that positive charge. How might you expect the activation energies be for all three pathways compared to benzene? They're all going to be higher. Which one's going to be the highest? The ortho-para pathways, right? So all of these reactions are slower than benzene. This is why we say it's deactivating. But why the meta pathway? Not quite as deactivated. So if we look at the diagram again, you can see both lines are higher than that of benzene alone. But the ortho-para pathway, ortho representing both the ortho-para pathway, are even higher because that positive charge sitting right next to that substituent. Whereas the meta pathway, still somewhat deactivated by induction, but not quite as badly as the ortho-para pathways. I think what might be good to end today, to kind of try it all together, we have like 4 minutes, is if you could turn to page 34 for a second.
Are we done?
Pardon me?
At 9:20 class ends?
Are we done at 9:20? Yes.
Yeah.
Yeah. And so we have, I'm looking at the time. Oh,
You have -2 minutes.
you know what? Okay, all right. So my bad. You're right. We are done. Forget that clock. We are done. We will do this next class. I went over time. Thank you, Aiden. Thank you for your kind patience as we try to navigate all this stuff. And for your trying to pay attention to this more dense